All right, I know everybody is super excited to start talking about kinematics equations. All right, so before we actually get into the kinematics equations that you've seen around the classroom, let's talk about the three that we have been using. All right, so we have our displacement equation, which is just our final position minus our initial position. We have our average velocity equation, which is that displacement over our time interval. And then we have our average acceleration, which is our change in velocity over that time interval. All right, so out of these equations, we see the big five variables that we're going to be looking at. All right, we see delta x, which is our displacement. We see our time interval. We see initial velocity. We see final velocity, and we see acceleration. All right, so what these three original equations don't do is they don't really show us a lot of relationships that are outside of the equations that are just used to figure those out. All right, so the difference between kinematics equations and the original equations that we have is that our kinematics equations take 4 out of the 5 variables that we have, and they show them in a way that gives us the mathematical relationships that exist in an object's motion. So they're looking at how displacement is going to affect acceleration. All right, so different things like that. All right, so what I want you to look at right here are our 4 kinematics equations. All right, do not worry. You will never, ever, ever have to memorize these. You will always be given these on a quiz or a test. They're always going to be posted around the room, okay, or on your quiz or test. So you do not have to memorize them. I repeat, you do not have to memorize them. However, you do have to know what each and every variable means, as well as have to be able to rearrange it to solve for any of the variables in it. All right, so I want you to look at each of these equations. All right, so let's look at this top left one. All right, we have V final, V initial, acceleration, and our time interval. So the one that we are missing, one variable out of the 5 that we are missing is our displacement. So in this one, there is no displacement. So we would use this equation if we were not given displacement. All right, in the top right, we're given V final, V initial, acceleration, and displacement. We are missing our time interval. All right, so we would use that one if we were not given time. All right, on our bottom left, we have displacement, V initial, V final, and our time interval. There is no acceleration here, so we would use this if we were not given acceleration. And then our last one, we have delta x is equal to, or we have displacement, initial velocity, time, acceleration, and then time again. So what we are missing here is our final velocity. All right, so each of these is missing one of the variables, but if you notice, there is one of the 5 variables that is in every single one of them, and that is V initial. All right, so V initial is in every single one of these equations. All right, so with the exception of that initial velocity, there's going to be one variable missing in each of these. All right, so we have been preparing you since last year for this time, okay? So because we have 4 different equations, technically 7 if we're including our 3 original ones, that have a lot of the same variables, we have to use our guess method. We have to use that guess method, especially these first 2. If you do not write down your givens and what you're looking for, there is no way that you are going to know which equation to use. Okay, so it is super, super important that you are using our guess method. All right, so let's move on to our first kinematics equation. All right, so we have our displacement is equal to 1/2 times V initial plus V final times delta T. So for this one, we do not have acceleration. We do not require acceleration to be able to solve for this one. All right, we have all of the rest of the 4. All right, so this is the one that we would use if we were not given acceleration. All right, so let's look at this first example. We have a race car reaches a speed of 42 meters per second. It then begins a uniform negative acceleration using its parachute and braking system and comes to rest 5.5 seconds later. I want you to find the distance that the car travels during braking, okay? All right, so the very first thing that we're gonna do is we're gonna list out all of our givens. All right, so our first one is going to be 42 meters per second. We know that if the unit is meters per second, then that is a type of velocity. Now, the reason that I underlined comes to rest, that's not a numerical given, but that is a very, very important given for us. All right, if we are coming to rest or if we start from rest, that is one of our givens. So for us, it comes to rest. We know that the velocity of something at rest is 0 meters per second. All right, so that's going to be another velocity. By the way, I didn't mention this on that first given, but velocity is a vector quantity, so we always need to include a direction with it, even as we're writing down our givens. All right, so because I did not give you a specific direction, we assume it's going in the positive direction. So that velocity is going to be a plus 42. Okay? So now we have 2 different velocities, all right? Well, we can't have 2 different velocities. So hopefully big red flags should be popping up right now. And that tells us that we need to differentiate between which one is the initial velocity and which one is the final velocity. All right, so the easiest way to look at it is the one that says comes to rest. All right, so that means that it was already moving and it came to rest. It stopped. All right, so that tells us that our 0 meters per second is our final velocity, which makes our 42 meters per second our initial velocity. All right, and then our last given is 5.5 seconds. We know that time is measured in seconds, so that is our time interval. All right, so those are all of our givens that we have in this problem. The next thing that I ask you to do is to find the distance, okay? So distance is a lowercase d. There is not a single lowercase d in any of our kinematics equations. So if I ask you for distance, what I am referring to is the displacement, all right? So we are looking for displacement. All right, so let's look at our givens. All right, we're given V initial, V final, delta T, and delta X. So the one that we are missing is acceleration. So the only kinematics equation that we can use is our first one. All right, so we use delta X is equal to 1/2 times V initial plus V final times delta T. All right, we do not have to rearrange this equation because it's already got our unknown isolated to the left over there. So all we have to do is just plug in our numbers. So we have 1/2 times V initial, which is 42, plus 0 times 5.5. All right, 1/2 of 42 is going to be 21. That's going to be measured in meters per second, and then we're going to multiply that by 5.5 seconds. All right, 21 times 5.5 is 115.5. Now, we are looking for displacement. The unit for displacement is meters. And we need to remember that displacement is a vector quantity. If you go back to all 5 of these original, or all 5 of our variables that we're going to be using, there is only one that does not need a direction, and that is time. So unless you are solving for time, your answer has to have a direction to it. All right, so we know that our displacement is going to have the same direction as our velocity, and our velocity is positive. So, I did not mean to make that green. Boop. Okay, so our displacement is going to be a positive 115.5 meters. All right, let's move on. So we have a car accelerates uniformly from rest to a speed of 6.6 meters per second in 6.5 seconds. I want you to find the distance the car travels during this time. All right, so our very first given says from rest. So it is speeding up from rest. So that tells us that our initial velocity is going to be 0 meters per second. 0 meters per second to a speed of 6.6 meters per second. Now, we don't use speed in kinematics, we use velocity. This is our final velocity, and velocity always needs a direction. So I did not give you a specific direction in the problem, so we assume that it's going in that positive direction. Okay, now our last given is 6.5 seconds, and we know that that is our time interval delta t. So those are our givens. I ask you to find the distance. Find the distance. So what we are looking for is our displacement. Yet again, we are missing our acceleration. So the only equation that we can use at this point is that first one. So delta x is equal to 1/2 times v initial plus v final times delta t. All right, so we have 1/2 times 0 plus a positive 6.6 times 6.5. Half of 6.6 is going to be 3.3 times 6.5 seconds. So 3.3 times 6.5 is going to give us 21.45. 21.45. Now, again, we're solving for displacement. We know the unit for displacement is meters, and displacement is a vector quantity, so we have to have a direction. And our displacement's direction will always be the same as our velocity. So our velocity is positive, so is our displacement. Okay? All right, easy peasy. Let's move on to our next equation. So we have V final is equal to V initial plus acceleration times our time interval. Now this one should look extremely familiar to you because we have actually already derived this equation from our original acceleration equation. All right, so we know that acceleration is the change in velocity over delta t, which means that acceleration is V final minus V initial over our time interval. All right, so these equations are the exact same equation. They are the exact same equation. So it doesn't matter which one you want to use. The first one is solving for V final. The second one is solving for acceleration. So they are both going to give you that same answer. All right, it just depends on which variable you are solving for. Okay, our third equation. If you look at this second one, we have no displacement. So if we were not given a displacement, this is the equation that we would use. All right, our third equation, we have delta x is equal to V initial times delta t plus 1/2 times acceleration times delta t squared. Now, there are a couple of things that we need to look at right here. All right, so the first thing is that we do not have any final velocity. So if we are not given V final, then this is the equation that we would use. Now, if we look at all of our equations, if we have the 4 variables in any given equation, we can rearrange any of those 4 equations to get whatever variable we are looking for. But if you are looking at this equation in particular, not only can you not use it to solve for v final because v final is not present in the equation, I would highly suggest not using this equation to solve for time. All right, so time is right here and it is right here. So you have time in two different places, and in one of those places, it's being squared. All right, so not saying that it's impossible. I'm just saying that we might not want to use that to solve for time. Unless, there's a big unless here. All right, we could solve for time using this one if V initial is 0. So if V initial is 0 meters per second, that's going to cross out this whole first part. And then at that point, we can use it to solve for delta t, all right, because delta t at that point would only be in one place. So unless V initial is 0, I would not use this equation to solve for time, all right? Or v final because it's not in it. All right, before we go to this example, I want to just go over the very last equation. This is the last of our 4. All right, so we have v final squared is equal to v initial squared plus 2 times acceleration times delta x. So there is no time interval in this one. So if we're not given time, this is going to be the only one that we can use. All right, so the other thing I want to point out is that I have reminded you that delta x is final position minus initial position. Now, the reason that we do that is that we are now at the point in the year where we can start taking former equations and plugging them into variables in a different equation. So for us, we could take x final minus x initial and plug it in to this delta x if that is what we are given. All right, so you're going to see a lot of that, especially second semester, but this is just the beginning. All right, so we do need to keep that in mind. All right, so now we have all 4 equations. Let's go back to this example. I love this example. All right, so we have a plane that starts from rest at one end of a runway that undergoes a uniform acceleration of 4.8 meters per second squared for 15 seconds before it actually takes off. All right, so let's go ahead and write down those givens. All right, if it starts at rest, that tells us that our V initial is 0 meters per second. It is starting at rest. Our next given is going to be our acceleration of 4.8 meters per second squared. Now, before we move on, we need to remember that acceleration has to have a direction also. Now, for acceleration, we can't just assume it's positive. We have to actually look at the velocity first, look at the situation. All right, so this plane is moving, or it will be moving, okay, at the end of a runway. And so we know that it's going to be moving. I did not give you a specific direction, so we assume that this plane is moving in the positive direction. Well, if it starts from rest, that means that it has to speed up in order for it to actually take off. So if this plane is speeding up in the positive direction, that means that that acceleration also has to be positive. All right, so speeding up, those signs have to be the same. All right, so that we do have a positive acceleration of 4.8 meters per second squared. And then our last given is our time interval of 15 seconds. All right, so those are what we were given. The first thing that I ask you to do is I want to know what is its speed at takeoff. All right, so if we know we're looking for a velocity, we don't use speed, we use velocity. All right, so what is its speed at takeoff? We already have initial velocity, so that means that we are looking for final velocity. All All right, now for this one, I know that I am not given delta x, and there is only one equation that does not have delta x in it, and that is our second one. So we use v final is equal to v initial plus our acceleration times our time interval. All right, we're looking for v final. V final is already isolated, so we do not have to rearrange the equation. So we can just go ahead and plug in our numbers. So we have 0 plus 4.8 times 15. Okay, so 4.8 times 15 gives us 72. Now, we're looking for a velocity. So velocity is found in meters per second. And velocity also requires a direction. So we have to look at where it's going. Again, we're assuming that it's going in the positive direction. So V final is equal to a positive 72 meters per second. Okay, so we just solved for V final. The second thing that I ask you to solve for is how long must the runway be for the plane to be able to take off? So we want to know the length of the runway, which is our displacement. We are looking for displacement here. All right, so at this point, we have all 5 variables. All right, so we can solve for displacement using any of the other 3 equations. So right here, you see that we used our first equation. There was no acceleration in that and got a plus 540 meters. Right here in the blue, we used the third equation and got positive 540 meters. And then down here in the green equation, we used the last one that did not have time in it and still got the same exact answer. So what I'm trying to get you to see is that if you have a couple of equations that you can use, it does not matter which equation you want to use. You can use any of them as long as you have all the variables for it. It's going to give you the same answer. Okay, so even though we did not use any of the same question or any of the same equations in these, it gave us the same exact answer every single time of 540 meters in that positive direction. Okay. All right, so let's go back to, all right, so delta X was a positive 540 meters. All right, so that's how long the runway had to have been for that plane to be able to take off. All right, let's go to our next example. So we have a person pushing a stroller that starts from rest and uniformly accelerates at a rate of 0.5 meters per second every single second. I want to know what is the velocity of the stroller after it has traveled 4.75 meters. All right, first thing that we are always going to do is we're always going to write down our givens. So if it starts from rest, yes, that's one of our givens. Our V initial is 0 meters per second. Remember, 0 will never need a direction, but it will always need a unit. I never want to see a naked number for 0. It always needs a unit. All right, so V initial is 0 meters per second. Our next given is an acceleration of 0.5 meters per second squared. Now again, acceleration is a vector quantity, so we have to be able to tell a direction. We can't just assume that it's going anywhere. We have to look at the velocity, the direction for the velocity, and also what's happening in the story or in the situation. All right, so this person is pushing a stroller. I don't give you a direction for it, so we assume that it's going in the positive direction. All right, so if this stroller starts from rest, that means that it has to speed up. So if we are speeding up in the positive direction, that tells us that our acceleration has to be positive. And then our last given is 4.75 meters. The only thing that we have that's measured in meters is our displacement. And we know displacement is also a vector quantity. So we have to add a direction to it. Well, we are assuming that this person is going in the positive direction. So it would be positive. And then I am asking you to solve for the velocity of the stroller after it has traveled that amount of distance. So we are looking for V final. V final is what we're looking for. All right, so the only variable that we are missing is delta t, which means we have to use that last equation. So we have V final squared is equal to V initial squared plus 2a delta x. All right, so we're solving for V final. Technically, we do not have to rearrange this equation because V final is to the left, almost by itself. The reason I say it's almost by itself is because it is being squared. We have to get rid of that square in order to get V final isolated. All right, and we should know that to get rid of a square, we have to take the square root of both sides. All right, now one thing that I want to reiterate is whenever we take the square root, it only gets rid of the square on that unknown. It does not get rid of the square over here. Okay, so that square stays, it just gets rid of the square on the unknown. All right, so our V final is equal to the square root of V initial squared plus 2a delta x. So that's going to be the square root of 0 squared plus 2 times 0.5 times 4.75. Okay, let's look at that. All right, so we have 0 squared. That's going to be 0. All right, so that one just cancels out. Plus 2 times 0.5. Well, 2 times 0.5 is 1. 1 times anything, 1 is a mirror, so it's whatever that other thing is. All right, so what we are looking at is just the square root of 4.75. So let's find that square root of 4.75. That gives us a raw answer of 2.179449472. All right, I do always want you to write out your raw answers. That has not changed. The only thing that has changed is that because we are looking at two-step problems, kind of like what we saw right here, all right, we had to use this in order to find this. All right, that's whenever sig figs get a little hairy. All right, so I'm not really worried about sig figs anymore, but I still want you to give me a good amount of decimal places. So by a good amount, I mean like 2 decimal places at least. So if we are looking for 2 decimal places, that means we cut it off after that 7. And that makes my final velocity 2.18. We know that velocity is found in meters per second, and we are assuming that the person is pushing a stroller in that positive direction. So remember, velocity and displacement have to have that matching direction. All right. So after this person has pushed this stroller 4.75 meters with an acceleration of 0.5 meters per second every single second, she is going 2.18 meters per second at that time. All right. So the very, very, very last thing that we are going to do. All right. So a race car accelerates uniformly from 18.5 meters per second to 46.1 meters per second in 2.47 seconds. All right, so let's go ahead. That's our given. Those are our given. So let's go ahead and write those down. All right, so we have 18.5 meters per second. Well, we know that meters per second is a type of velocity. We need to know that velocity is a vector quantity, so it does need to have a direction. Again, I did not give you a direction, so we assume it's going to be in the positive direction. Our next one is 46.1 meters per second. Yet again, that's another velocity. And again, we're going to assume it's going in the positive direction because I did not give you a direction. All right, now we can't have two just V's. We have to determine which one is initial and which one is final. So whenever it says from this to that, all right, the from is going to be your initial, the to is going to be your final. And then we have 2.47 seconds. That is going to be our delta t. All right, so those are our three givens. I ask you to determine the acceleration. So we are looking for the acceleration of this car. All right, now the only thing that we are not given is our delta x. So we go back to the drawing board. We look at all of our equations. We know that the only one that does not have delta x is our second one. So we have v final is equal to v initial plus acceleration times delta t. Now we are trying to solve for acceleration, so we need to rearrange this equation. The first thing that we're going to get rid of is that v initial. It's being added, so we have to subtract it. So we have v final minus v initial is equal to acceleration times delta t. Again, still trying to get acceleration by itself, so we need to divide both sides by delta t. So acceleration is v final minus v initial over delta t. Huh, that looks kind of familiar, right? Da, 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 da. It's our original acceleration equation. All right, so if you can just remember that that is the same thing as our acceleration equation, you could have skipped all of that and just written out this equation. All right, so now that we've got it rearranged, we can just plug in our numbers. Now, the only difference between this one and all the rest of our problems is that we are not starting from rest or coming to rest. So both of our velocities have numerical values other than 0. All right, so it doesn't mean anything. It just means that we can't take the easy way out. We just got to plug it in. All right, so we're going to pull it up here. We're going to plug it in up here. So that's going to be 46.1 minus 18.5. Notice I have put those directions in there still. Over 2.47. All right, so that's going to be 46.1 minus 18.5. divided by 2.47. All right, so that's going to give us 11.17408,907. Okay, again, I usually want 2 decimal places, so my acceleration would be 11.17. So that's our numerical value. We know that the unit for acceleration is meters per second squared. And then we need a direction. So we can't just assume a direction. We have to look at velocity, which is positive, and then we have to look at the actual situation. So if we went from 18.5 to 46.1, that meant that we were speeding up. So we're speeding up in the positive, which tells us that that acceleration is also positive. Okay, so that's the first thing that I asked you to find. The next thing is the distance that it traveled. All right, so we are looking for delta x again. We're looking for delta x again. I don't know why I just did that. All right, so again, I want you to look at all the 3 other equations that have delta x in them. So our first one, delta x is equal to 1/2 times v initial plus v final times delta t. All right, we don't have to rearrange this. We can just go ahead and plug it in. We have 1/2 times 18.5 plus 46.1 times 2.47. Okay, so that's 18.5 plus 46.1 times 1/2 times 2.47. All right, that's going to give me a raw answer of 79.781. I want to pause right there. Let's move on to the next one. All right, our next one is delta x is equal to v initial times delta t plus 1/2 times the acceleration times delta t squared. Again, we do not have to rearrange, so we can go ahead and plug in our numbers. So that's going to be 18.5 times 2.47 plus 1/2 times 11.17 times 2.47 squared. All right, that's going to be 18.5 times 2.47. That's going to be 45.695 plus, we're going to do 2.47 squared first, and then multiply 11.17 times 1/2. That's going to be 34.0735, 265. Add those together. Okay, we get a raw answer of 79.7685265. Okay, now let's go to our last equation, which is V final squared is equal to V initial squared plus 2 times the acceleration times delta x. All right, again, we're solving for delta x, so we have to rearrange this one. Whenever we are isolating a variable, we always start from the furthest away from that variable, working our way in. So the first thing that we're going to get rid of is that V initial squared. All right, so it's being added, so we have to subtract it. So V final squared minus V initial squared is equal to 2a delta x. Now I have to get rid of 2 times the acceleration by dividing. Okay, so delta x here is equal to V final squared minus V initial squared over 2 times the acceleration. So that's going to be 18, nope, sorry. Not that it matters, I just like having it right. All right, so we have, oh, it does matter. This is a minus. All right, so 46.1 squared minus 18.5 squared over 2 times acceleration, which was 11.17. Okay, so we're going to take this piece by piece. 46.1 squared, 18.5 squared divided by 2 times 11.17. Okay, we should get 79.81020591. All right, so let's look at these 3 raw answers. Okay, so if we are looking at just the raw answers, then no, we do not have the exact same answer. But if I wanted you to take it to the near, or to just one decimal place for this one would be 79.8 meters in the positive 79.8. This one would be positive 79.8 meters. The last one would be positive 79.8 meters. So with our first one, whenever we did all the different ones, our answers were perfectly the same. All right, they were all 540. Like that was the raw answer, that was the final answer. But with this one, all right, with this one, the raw answers were not necessarily the same, but whenever we round to that first decimal place, all right, they are all the same. So again, it does not matter which equation you use. All right, they're all going to give you the same equation. All right, we're going to do more practice with kinematics equations before we get into vertical acceleration. So if you have any questions at this point, you know where to find me.